This lab is about measuring the absorbance of a reaction between crystal violet and sodium hydroxide, and from here determining the rate law of the fading of the crystal violet. Before performing this lab, be sure to be wearing safety goggles. In the lab, 25 micromolar crystal violet, 0.2 molar sodium hydroxide, distilled water, cuvettes, a colorimeter, a computer, 5 to 10 milliliter graduated pipettes, and a pipette bulb/pump were all used. Once all of the materials are prepared to be used, one can compare the absorbance with the concentration of crystal violet. As with the reaction of crystal violet and sodium hydroxide, its color fades. After the calibration curve is made, the reaction may proceed. The concentration can be found from the data received from the colorimeter. Finally, the rate law can be determined by analysis of the concentration graphs. In Figure 1, for each of the dilutions, the value of the crystal violet increased each time by 2 to increase its concentration for each different sample in each reaction. The total volume for each sample was to be about 10 milliliters, so when the crystal violet's volume was increased each time by 2, the distilled water's volume was decreased each time by 2. The volume of the sodium hydroxide for each sample was derived from using a ratio of sodium hydroxide to crystal violet of 4 to 1 because it was preferred to have sodium hydroxide in excess throughout the reaction. In Figure 2, the absorbances were received from each different concentration of crystal violet being tested in the colorimeter to create the calibration curve. Clearly, as the concentration increased, the absorbance increased. From this information, the calibration curve was able to be created, giving a slope of about 0.1648. Finally, in Figure 3, the absorbance was recorded during the reaction of sodium hydroxide and crystal violet. Once starting the reaction in a cuvette, it was placed into the colorimeter and the absorbance was read. Throughout this process, the absorbance was collected every second, but only displayed on the data table every 50 seconds until the reaction was near complete at about 600 seconds. At this point, the absorbance was at 0.001 and not changing anymore, which indicated the reaction being complete. Overall, as the reaction occurred, the absorbance decreased as the crystal violet faded to a clear color. The initial concentration of crystal violet used was 20 micromolar. This concentration was chosen because it would allow for a reaction rate that was fairly quick and an absorbance that was close to 1 but did not exceed 1.
10 milliliters of 5, 10, 15, 20, and 25 micromolar of CV were produced using the distilled water and 25 micromolar of standard solution of CV. To dilute these solutions, M1V1 equals M2V2 was used. For 5 micromolar, 2 milliliters of CV were used. For 10, 4 milliliters were used. For 15, 6 milliliters were used. For 28 milliliters were used. And for 25, 10 milliliters were used. Water was then added to fill the solutions up to the 10 milliliter mark. Then a calibration curve was created for each solution's absorbance levels. Using the slope of the calibration curve, the concentration of the CV was determined.
An important component of computing the reaction of hydroxide and crystal violet is graphing data points. Before you proceed with the reaction of crystal violet in an excess of hydroxide ions, be sure to construct a calibration curve. Once the calibration curve is complete, react the crystal violet with the sodium hydroxide. When the reaction has gone to completion, divide the absorbance by the slope of your calibration curve. Again, with units canceling out, this value will yield the concentration of crystal violet. So here's an example of data points you could achieve from doing the lab. So as you can see, time is going to be all in one column. Now going down, you can see it goes very far. This is measured in seconds and it goes all the way to 600. I won't take you all the way through, but same goes for absorbance. You can set the interval with the computer program you're using. So after you get the absorbance, you can use the formula described earlier to find the concentration. And of course, you can compute it with every other value, and using the Excel functions, you can definitely insert a formula for these. And the same goes for the natural log and the 1 over concentration. This is going to help you determine the reaction order. So the data here is shown from the previous points, and the fact that CV with respect to time is not linear means that the reaction order is not 0. Moving on to the right, natural log of the concentration versus time was graphed here. The linear relationship shows that it is first order. Now, just to ensure that the reaction isn't second order, 1 over CV was graphed, and because it is not linear, the most valid conclusion is that the reaction is first order based on this linear graph. The trend line is barely visible since it basically intersects with all the data points, and the slope here is negative 0.0058. So the rate law from the lab is given here. And since we have 0.0058, we can plug that into the K value. and since ln versus time is linear, the order is 1. Since the reaction rate is first order, 0.0058 must be in seconds to the negative 1. This value times the concentration will yield the rate, micromolar per second. Here is the pseudo-rate law.
A source of error in this lab was that there were scratches and cracks on the cuvette. A crack would allow for more light to go through and therefore create a higher absorbance. A solution to this problem could have been to purchase a new cuvette with little to no scratches that may possibly interfere